Right, hello everyone. I'm going to lead you through Unit 4, Lesson 4. We're going to solve systems with absolute value and linear equations algebraically or analytically. So let's take a look at how this process works. This first page in your notes is almost like a textbook page where it's got step-by-steps of how we would go about solving uh, a system like this, which I'll come back and explain what that is. And it talks about what these solutions represent. So this is a great page to use as a resource as you work through this lesson and as you work on preparing for your assessment down the road. So don't ignore this page, use it to help you, read through it a couple times, highlight the important pieces. In fact, we're gonna do that right now anyway. So here's what we're trying to do in this lesson. We're trying to figure out if I've got an absolute value equation like what we see here of f of x, where might the solutions to that system with this equation of g of x equals negative 3x plus 8. So really what we're doing, if you think back to systems, we're looking for where this graph might intersect with that graph. That's what we're doing when we're checking to see what the solutions are between two different equations. Where do their graphs intersect? Now, working with absolute value can be a little tricky. So one thing that we like to do, and one thing that we're going to have to do, is we're going to have to take this absolute value equation and think about it as two different linear equations, which is really a piecewise function. And we talked about that in our second unit. Now, we don't need to go real in depth here. Really what we need to know is every absolute value equation can be written as a positive, this would be the positive branch right here, a positive line, as well as a negative line. Notice that nothing's different about these linear equations to this absolute value equation. We have this same point right here, the negative 2, negative 4, negative 2, negative 4, just a negative slope and a positive slope. This is what allows us to solve where this part of that absolute value equation might intersect with this line, and then where this part of the absolute value equation might intersect with that line. So this point right here, the negative 2, negative 4, that is the vertex. So whenever we're doing this down the road, we're going to see this absolute value equation. We're going to write it with a negative slope and a positive slope, and then take each one of those and set them equal to our other equation. So there's lots of algebra going on here. So step 2, this is where you set up the equations and solve. So as you can see, this is the negative slope equal to that linear line. And then we have the positive slope equal to the linear line. The following steps are working to get x by itself to come up with two different x values. So what this is saying is we might have two places for where the absolute value equation intersects with that linear equation. So right now we're thinking they intersect at x equals 10 and x equals 2. Again, you can follow these steps to see how that algebra works out. Now, just because we get two x values doesn't mean they both work. The next part of this is to verify that both values of x are in fact solutions. So what we've got to do with those x values is we've got to plug both of them back into the original f of x, so the original absolute value equation, and the original g of x, the original linear equation. So when I plug in 10 back into the f function or the absolute value function, I get 14. But when I plug it back into the linear function, so g of 10, I get negative 22. These are different y values, which tells us that x equals 10 is not a solution. When we are plugging these x values back in, if they are in fact solutions, we should get the same y values. And that's what we're seeing when we plug in 2. If I plug in 2 to the absolute value function, I get a y value of 2. If I plug in 2 for the linear function, I get another y value of 2. So this tells us that x equals 2 is a solution, and the solution itself is the full point, so 2 comma 2. If we were to graph that, I can see that. So this absolute value is that same f of x equation at the top of the page, and this is our g of x function. And so we can clearly see that this graph intersects at 2 comma 2. So all the algebra is working for us to find that specific point. Yes, it would be much easier to graph it, but we're going to work on solving it without the graph. So this is explaining what I just went through. Again, you can use that as a resource. And the last couple things. This is a very tedious process. If we can make a quick sketch of the system, it really helps us narrow down what do we need to focus. And I'll show you what I mean by that as we go through a few examples. Okay, so again, this is a great page to use as a resource as you work through the entire lesson. So let's do an example together. Now, like I said, if we could come up with a graph, we could get an idea as to where might this absolute value equation intersect with this linear equation. We might even be able to determine, do they intersect once, twice, or 0 times. This one might be a little bit tricky to graph. In fact, we'd have to use our similar or our ways of taking absolute value equations and rewriting them where X is just a +1. So I'm going to skip that part here and let's just jump into the actual algebra. We'll talk more about the graph here because this one, I know it's really easy for me to graph f of x and g of x and make a quick sketch of that. So let's talk about the algebra first, and then we'll talk about the graphs here in a second. So if I'm trying to find where this absolute value equation intersects with this linear equation, the first thing we need to do is we need to come up with splitting up f of x to be 2 different equations. So really what we want f of x to be is we want one branch to be positive. So I just put 3x plus 2. All I'm doing there is changing the absolute value brackets to be parentheses. This is that positive branch of the absolute value equation that I was referring to on that first page. The other branch, it's the same thing. So I put everything in absolute values in parentheses, but we want that to be our negative branch. So I'm going to put a negative out in front. So now I've taken this absolute value equation and split it up to be a positive or linear equation and a negative linear equation. So what I'm going to do is I'm going to take 3x plus 2, or that positive branch, and I'm going to set it equal to our linear equation of 4x plus 5. And we're going to solve for x. So let's do that real quick. I can subtract 3x to get 1x, right? 4x minus 3x is 1x. I can minus 5 from 2 to get negative 3. So I get one x value of negative 3. Might be a solution, it might not. We need to check that, which we'll do in a second. So this was me setting my positive branch equal to the linear equation. Now I'm going to take that negative branch and set it equal to the linear equation and come up with a second x value. So this is negative 3x plus 2 equal to the linear equation of 4x plus 5. With this negative, I'm going to distribute that to make this negative 3x minus 2 equals 4x plus 5. And then again, we're going to work on trying to get x by itself. So I can add 3x, that makes this 7x. I can minus 5 to make this negative 7. And I get x equals negative 1. So right now we have these 2 different x values. And again, one might work, both might work, and it's possible that none of them might work. So let's figure that out. So once we have these x's, we need to take this value of negative 3 and plug it into f and g and see if we get the same y value. So f of negative 3 would be 3 times negative 3 plus 2. This would be negative 9 plus 2, or the absolute value of negative 7. Remember, when we're taking the absolute value of numbers, we just simply make them positive because we're measuring its distance from 0. So f of negative 3 gives us 7, which means when x is negative 3, y is 7. Let's see what we get for g of negative 3. G of negative 3 is 4 times negative 3 plus 5, which is negative 12 plus 5, and I get a y value of negative 7. These are not the same value, right? We're getting 7 in both cases, but in one of them I'm getting a positive 7 and a negative 7. So what that means is negative 3 is actually not a solution. And the word for that is that it is extraneous, meaning we solved to get this x value, but it is in fact not really a solution. So I can identify as extraneous, but in reality, we don't really care about that, meaning it's not a solution. So more likely, negative 1 will be a solution, but we still need to verify that because it's also possible that none of these work. So f of negative 1 is the absolute value of 3 times negative 1 plus 2. The absolute value of negative 3 plus 2, which is the absolute value of negative 1, which equals a positive 1. So f of negative 1, or when x is negative 1, we get y to be positive 1. G of negative 1 is 4 times negative 1 plus 5, which is negative 4 plus 5, which is a positive 1 as well. That's what we're looking for. We need these y values to be the same when I plug in the x value. That is confirmed that this is a solution. So the last piece is putting it all together. When x is negative 1, the y value is positive 1, and that is our 1 point of intersection and the only solution to this system. We could absolutely graph these and confirm that by seeing that they intersect at -1, 1. All right, so that's kind of the basic process. And when we have absolute value and we're checking to see when it's equal to a linear equation, that's the same procedure that we're going to do. When we get down here to an absolute value equal to another absolute value, there's a little bit more we're going to have to worry about. So before I let you hit pause and work through number 2, let's look at what the graphs might look like and how we can use that as a tool to kind of guide our algebra. So I can graph f of x pretty easily, right? I'm just going to draw a quick sketch. Notice I'm not even going to put numbers on there. I'm just literally making this a small graph. I know that this absolute value function would have a vertex right 1 at +1. I know that it would have a slope of 1. So it's going to open up like something like that. I'm not actually counting out the slope. I'm just doing a quick sketch. 5x plus 10. Well, I'm going to start at the y-intercept of up 10, which is quite a bit. And then it has a pretty steep slope of 5. So when I draw that steep slope, I'm seeing that this intersects 1 time. So this graph is telling me there's probably 1 point of intersection. When I look at which branch of the absolute value it's intersecting with, this is actually the negative branch. And how do I know that? Well, if I hide the right branch here, this line right here, right, that has a negative slope. It is going down as I move to the right. So when I get to my algebra, I know that I need to take the negative branch of my absolute value and set it equal to the linear equation. Now, we don't always have that luxury. So it still might be worth our time to do the plus or the positive slope of the absolute value and still set it equal. But this can kind of limit a lot of that work. So take that as you will. What I'm going to have you do now is have you hit pause, and I'm going to have you work through number 2 and see if you can come up with the 1 point of intersection based on the work we just did. All right. Well, here's your work. And in this situation, we do get some fractions. Don't let that steer you away from continuing with the problem. You can always take the fractions and convert them to decimals. You can do that on your calculator pretty easily by taking that fraction, and remember that fractions are division problems. So if I want to find the decimal for -9/6, I do -9 divided by 6, and that's -1.5. You can use -1.5 as you proceed with work. Okay, same deal with -11/4. If I want to find what that decimal is, I can do -11 divided by 4, and I get -2.75. So if you need to convert these fractions to decimals, feel free. And as you can see, I do that at some point, okay, with both of these. So it does not matter if you use fractions or decimals. For a lot of us, it's easier to use decimals because we keep that in the calculator. And if you have questions about how to do any of this, ask your specific teacher. These are things that we want to work on because we're going to get some fractions here in this lesson and a bunch of fractional answers down the road. So like I said, when we looked at our graph, we knew that this positive value or the positive branch of the absolute value equal to the linear was not going to work. And I saw that by getting an x value of -11/4 and getting 2 different y values that are not the same. So that did not work just like we expected. So I didn't even need to do that work because of what the graph showed me. And I recognized that the negative branch of the absolute value only intersected with the line. I did not need to even worry about this negative branch here, or that positive branch, excuse me. So all this work was not necessary because of me graphing the equations. The actual solution, when I take the negative branch equal to the absolute value, I get x equals -9/6, which is -1.5. And when I take that y value and plug it in, or that x value and plug it back into both equations, I get y to be 2.5 in both cases. So our solution is -9/6 or -1.5, comma 2.5. All right. Well, those would be what I would consider the more straightforward and more simple systems that we're going to solve in this lesson. The more tricky ones are when we have an absolute value equal to an absolute value, because now we've got a lot more to check. Each one of these absolute value equations has a negative branch and a positive branch. So let's start by how would we write these as 2 linear equations? Well, f of x, remember, all we're going to do is change the absolute value to be regular parentheses. So this is our positive branch for f of x. The negative branch, I still just change the absolute value brackets to normal parentheses. And I'm just going to throw a negative in front of those parentheses. It's that simple to make that negative and make it a linear equation. So why don't you do this? Why don't you hit pause real quick? And why don't you write the negative and positive branches for this absolute value equation? Once you've got them done, go ahead and unpause. All right, well, it should have been real quick. And really, as we see this equation, the first one I might write is actually the negative, because that's what the equation looks like, right? If I just switch these absolute value brackets to parentheses, that gives me that negative branch of that absolute value equation. And then positive, I just change the sign to be positive. Those absolute value brackets are still parentheses. So here's what we need to check. We need to check when the positive branch does it intersect with the positive branch of the other absolute value and the negatives. We've already got to check 1, 2 things. We've got to do the same thing with this negative branch. And does it intersect with the positive and negatives? We have 4 different things we need to check. This is why it gets tedious. So let's set this all up. I've got a positive branch equal to another positive branch. So this would be x plus 6 equal to x plus 1 plus 10. So that's my positive equal to a positive. We're going to get a positive equal to a negative. So let's use the same positive here. X plus 6 equal to the negative branch of the other absolute values, negative x plus 1 plus 10. So there's 2 of our 4 equations we got to check. Then let's take our negative branch of f of x and set it equal to the positive of g of x. So that's negative x plus 6 equals x plus 1 plus 10. And then our last one, we're going to take both negatives and set those equal to one another. So negative x plus 6 equal to negative x plus 1 plus 10. So we've got a lot of work to do here. This is, again, why it would be really helpful if we could come up with a quick sketch and identify which one of these do we not need to worry about. Because we might get 1 solution, we might get 2 solutions. It's even possible we get no solutions. So I highly encourage that we make a quick sketch of the graph. Let's pretend like we don't have that luxury this time around, and let's solve for all these values. So right now, I'm going to take all these equations and I'm going to solve for x. In fact, why don't we have you hit pause and work through that? That'll also save on some time for this video. So once you hit unpause, I'll have all of the x values for each 4 of these intersection points. All right, so we actually got a little lucky here, because in 2 different situations, when I try to solve for x, the x's go away, right? In this first positive equal to another positive, when I have an x on both sides and I subtract x's, they cancel each other out. So I'm left with 6 equals 11, meaning this does nothing for us. So we don't even need to check those y values, which saves us some time. That's not going to always work out that way. Typically, you're still going to have to take whatever x value you get here and plug it in for the x's and find to see if the 2 y's match up. Okay, but we also had that same thing over here. So really convenient for us in this particular case. So what I came up with is 2 different x values, one from each positive and negative branch of the 2 different equations. I went ahead, since they were fractions, I convert them over to decimals just to make it a little bit easier for me to work with. So now that we have these x's, we need to take those x's, plug them back in, and see what we get for y. Again, since you have seen me do that process, why don't we have you hit pause, and when you press play again, I'll have those y values ready for you. Right, well, here are the y values that you should have gotten, 7.5 and 7.5 in both f and g, telling us that we have a solution of 1.5 comma 7.5. So we've already found 1 point of intersection. For the other x value of negative 2.5, when I plug that in, I'm again getting the same y value, this time at 8.5. Once again, finding another point of intersection. So what that tells us is these 2 graphs intersect twice. Once where the positive branch of f of x intersects with the negative branch of g of x, and then the opposite, negative f of x and equal to positive g of x. Again, if we could graph this, it could be really helpful. In fact, let's do that real quick, just so I can, maybe we can pick up on it and use this in the future. So I wanted to make a quick sketch of this. I knew that f of x, being absolute value of x plus 6, starts up 6. got a slope of 1. So something like that. Again, doesn't need to be perfect. Gives me some direction. Negative x plus 1 plus 10 tells me I need to go left 1 and up 10. So that's up by quite a bit. And then that's a negative slope. Show me that there's 2 points of intersection. And I can see this is my negative branch. This is actually that positive branch. Okay, and same thing over here. So I can just by this graph, if I had this before I started, I wouldn't have even needed to do that work. I would not have even needed to do that work. And I would just need to do positive equal to negative and negative equal to positive. So using the graphs can be so powerful and save us a lot of time and effort. All right, well, that concludes this video. You have lots of practice with this lesson. Practice is key. If you are not trying these problems, they're going to be difficult. But if you try them, you'll get the hang of it. All right, thanks for watching and have a great rest of your day.